I'm Richard Hollingham. Welcome to the Planet Earth podcast. This time I'm at the British Antarctic Survey in Cambridge to meet one of the scientists who discovered the hole in the ozone layer. Also, how studies of starlings on one of Britain's most remote islands could help conserve other bird species. And we head into the skies above Canada to study smoke.
There are some indications that we might be starting to see something now. So fingers crossed this is going to be the plume that we're looking for.
In May 1985, British Antarctic Survey scientists Joe Farman, Brian Gardner and Jonathan Shanklin described in the journal Nature their observations of large losses of ozone over Antarctica. The ozone layer acts as a sun shield to the Earth, blocking ultraviolet B, which can cause skin cancer. Just over 2 years after the publication of that paper, governments around the world signed up to the Montreal Protocol to phase out the production and use of chlorofluorocarbons, CFCs, and other ozone-depleting chemicals. All sorted then. Well, not only is there still an ozone hole over the Antarctic, this year ozone loss over the Arctic was so severe that for the first time some people have described it as an ozone hole. So what's going on? Well, with me in one of the laboratories here at the British Antarctic Survey are Jonathan Shanklin and also atmospheric chemist Anna Jones. Now, Jonathan, you were carrying out your study at the Halley Research Station, that's on the Brunt Ice Shelf, and you've got one of the original graphs here.
We've got the data from Antarctica, which I'd plotted up. And one of the key things was that we could see something systematic going on in our data.
So let's look at this graph, and it's plotted by hand. Time before computers would do this.
Drawn on paper with pencil and a ruler to draw the best fit line through the data. But the point is, anybody can see that something's happening. You can see ever so clearly that ozone amounts are going down. And that was really absolutely key. Once you have something systematic, then something must be causing it. And the question was, what?
This is the Nature paper we've also got here. And this is interesting because figure 2 of the Nature paper, again, obviously originally drawn by hand and then printed, you made a correlation between this decline in ozone and CFCs.
Yes, there'd been thoughts that CFCs could affect the ozone layer for some time, but the predictions were that they should be affecting the ozone layer high above the tropics. What we actually found was low above the Antarctic, quite a different place, but because there's been this expectation that chlorofluorocarbons could affect the ozone layer, we thought, well, this is probably the case. And so when we plotted the graph, we guided the eye by choosing the right scale so that at a glance you could see that there was a correlation between ozone amounts declining and the CFC amounts going up.
Okay, so the Montreal Protocol is signed. I mean, a huge success in terms of environmental treaties, just getting that done 2 years after your discovery. Why then is there still an ozone hole over the Antarctic and now what many people are describing as an ozone hole over the Arctic as well?
The Montreal Protocol has been incredibly successful. Today, every single one of the UN member states has signed up to it. But these CFCs are very, very stable. They persist in the atmosphere a long time. And although it's very clear that we've passed the maximum in the atmosphere, the amounts are going down, the treaty is working, there's still so much around that ozone destruction can take place whenever the conditions are suitable. Now, in the Antarctic, they're suitable every year. In fact, this year we've had one of our deepest and largest ozone holes actually on record. Also, the conditions were suitable in the Arctic this year.
So, Anna, if I can bring you in as well. Now, CFCs are a greenhouse gas, so getting rid of them, that's going to be a good thing. There's another link, though, isn't there, between ozone depletion and global warming?
There is, and it basically comes down to stratospheric temperatures. Greenhouse gases warm the surface, but they cool the stratosphere. Ozone in the stratosphere, if it's there, it will warm the stratosphere, but once you get rid of the ozone, it won't warm, so that it's cooler. So both of these effects, global warming and stratospheric ozone loss, will cool the stratosphere.
And why does that matter?
People have now realised But cooling the stratosphere is affecting the air circulation patterns down on the ground, and that actually feeds into all sorts of other phenomenon which have really been quite surprising. CO2 uptake by the Southern Ocean, sea ice extent, and the temperatures on the ground.
So all this points to much greater complexity, Jonathan, than perhaps you first imagined when you plotted this very simple graph.
Yes, when we first made the discovery, we thought, well, this is a pretty obscure part of the world. It's not going to have a global impact by any means, but it is a lesson in how quickly we can change our atmosphere. This happened in the space of about a decade between it being detectable to being a full-blown ozone hole.
Let's go back then to this paper, this graph, and the Montreal Protocol, which is given as an example of a huge success when it comes to these sorts of treaties. Is that repeatable when it comes to global warming, to climate change?
There are differences. With the CFCs, just about everybody was on side. The manufacturers were quite happy to switch to a different product. It was very easy to switch to a different product. Also, the public don't like holes. So calling it an ozone hole, that must be bad just because of the name. And also the link between increased ultraviolet light and cancer. And again, cancer is one of our real banes of today's society. So if something's causing cancer, we've got to get rid of it. So everything worked in favour of doing something about the ozone hole. With the greenhouse gases, it's much harder. Greenhouse warming sounds nice, but secondly, it will take a very big change in lifestyle for individuals to reduce their dependence upon substances that get converted into carbon dioxide. And also the manufacturers, the industry, the oil industry in particular, is rather reluctant to stop selling oil. There's no cheap alternative that could be widely sold. I think we'll be lucky to get a treaty that's effective like the Montreal Protocol was.
Well, Jonathan Shanklin and Anna Jones, thank you both very much. This is the Planet Earth podcast. For more news from the natural world, do visit Planet Earth online. You'll also find us on Facebook, where we've put some pictures up of our recording here today, and you can tell us what you think. It's that time of year when all right-thinking birds head somewhere warmer until spring. But not the starling. This noisy, chattering bird sticks around, even during the harsh winters on Fair Isle in Shetland. Famous for its patterned sweaters, Fair Isle is one of Britain's most remote inhabited islands. Just 3.5 miles long and 1.5 miles wide, it doesn't even have any trees. Fair Isle does, though, attract scientists, including Daisy Brickhill from the University of Aberdeen, who studies the population of Shetland starlings. Sue Nelson met her to discover how the results of her work will provide an insight into conserving all kinds of other birds.
They're not quite the same starlings as we get on the mainland, so they're a little bit different. They're actually a separate subspecies. On the mainland, we get what we call a common starling, which is its fancy Latin name is Sturnus vulgaris. On Shetland, we get Sturnus vulgaris zetlandicus, which is the old word for Shetland. So they're actually slightly bigger than our starlings on the mainland, and they've got slightly longer bills, but you definitely still recognise them as a starling. On the mainland, of course, we know that starlings can nest in trees, and they've got lots of available nest sites to go along with. But on Fair Isle, there's basically nothing. There's a few sort of scrubby shrubs. And so as a result, the starlings have become very creative, and they started nesting in little broken down stone walls that were set up by the crofters, the farmers on Fair Isle. That's brilliant for us as researchers, because it means we don't have to shimmy up trees to study them.
Now, you're interested in not just the population of these particular starlings on Fair Isle with no trees, but also where they are as well.
What's really important is where the starlings choose to nest or where they choose to breed, because that can have a really important effect on the risk of extinction of the whole population. So if you've got a situation where, let's say, we've got really high quality nest sites, and by high quality I mean enables the starling to produce a lot of chicks, enables them to survive well, and we've got lower quality areas, maybe there's less food, they can't raise as many chicks. So if we've got these high and low areas, you imagine during a population crash, we've got very few individuals. If those starlings are canny, if they sit there in their low quality accommodation and they look up the road and they realise there's a mansion going free and they zip up the road to their mansion, That can mean that they'll then raise lots of chicks, they'll survive really well. You can see that that would mean that the population is then buffered against extinction, because at low densities we end up with population of starlings in very good situations, and so then the population will slowly start to rise again.
When you come to an island like Fair Isle, though, that has no trees, it's remote, it's surrounded by, as all islands are, sea, but in this case quite unforgiving weather conditions as well. What would you discern as a high-quality mansion on an island like that for a starling?
Starlings feed on little grubs found in the roots of grass. On Fair Isle, in the north, it's quite heathery, it's a little bit higher, and so we might expect that because there's less grassland up here, it's mainly dominated by heather moor, life would be a little bit harder for the starlings. And in the south, it's croftland, it's farmland, there's lots of pasture for livestock and that kind of thing, and we might expect that the starlings do a little bit better. Interestingly, in my first set of analyses, I found that the starlings in the far north really do very well. They actually do the best out of the whole island. So we've got a bit of a mystery going on there. And so what I'm looking at the moment is I'm sort of pretending to be a starling, trying to work out what makes a good starling area, because like you say, it's obviously not as obvious as I thought it was.
But then that's great, isn't it? Because for anybody who's interested in conservation, this means you can't necessarily go on what might be your gut instinct.
Yes, you definitely have to test these things and have a real proper look at what really is important to the breeding of these animals. So at the moment we've taken little core samples around some of the nest sites to look at the density of these little bugs that they feed on, in the hope that we can make sense of that, because maybe, you've got possible explanations like the grass that's next to heather is actually got richer amounts of bugs or something like that, and something that's not immediately obvious to us as humans.
How do you keep an eye on the numbers of these starling populations?
Every year we go to Fair Isle, and during the breeding season we look for nests. Once we've found these little nests, we gently remove the stones that cover them, and then we put our hands in and we take out the chicks very gently. We keep them warm the whole time, and what we then do is we give them very, very excellent bling. We give them 4 rings. We give them a metal ring. In fact, I can show you.
Oh, you've brought a little polythene bag here, transparent little bag of what look like children's beads.
Every time it looks like we're going off to do a craft fair.
I can see why, because they're red, yellow. Are they metal or plastic?
Actually, a combination. We give each starling 1 metal ring, which has got a unique number on it. These metal rings are given to us by the British Trust of Ornithology, who are in charge of the ringing all over Britain. So there's no other starling in Britain will be ringed with this particular number. And we then give them 3 of these very gaudy colour rings, and every bird has an individual combination.
So how will the work that you're doing here, we've touched on it a little bit already, apply to other bird populations as well?
That's really what I'm trying to do on Fair Isle, because it's nice knowing about the starlings on Fair Isle, but you want it to apply to other populations. What we're really hoping is that, because I'm looking at quite a fundamental aspect to a population, the fact that some places are good to breed in and some places are not, you can see that that would be important to populations of mammals, populations of all kinds of different birds. So you can see that that would be important across the board. So we're really hoping that this study will at least add to the evidence of how populations work and how risk of extinction can vary.
Daisy Brickhill from the University of Aberdeen talking to Sue Nelson. It's hard to recall, but earlier this year temperatures in the UK were higher than the Sahara, and at one stage a rash of forest fires erupted across the country. Forest fires can be a mixed blessing. They're nature's way of promoting new growth, but pollution from the soot or black carbon is estimated to kill more than 1 million people around the world each year and is a major contributor to global warming. Sarah Moller from the Atmospheric Chemistry Group at the University of York studies nitrogen oxides in the atmosphere and their relationship with ground-level ozone. Nitrogen oxides are formed anywhere where fuel is burnt, including forest fires, and at ground level, ozone is a pollutant linked with lung diseases. Well, over the summer, Sarah flew on a UK research aircraft over the eastern coast of Canada as part of the BORTAS project to assess the impact of forest fires. Why Canada? Well, emissions from forest fires in North America can affect the lives of people thousands of miles away in the UK and Europe. Here's Sarah's audio diary.
It's 7 o'clock in the morning and I've just arrived at the aircraft for power on before the flight. So we're taking off today at 11 o'clock, and so power goes on 4 hours before that so that we can get all the instruments warmed up and ready for flying.
Got the flight brief and some plots on there, so we ascend to 25,000 feet for our first leg.
It's now 1 hour before takeoff and we've got the science briefing. So in the briefing we find out where we're going to fly, where we're expecting to see the plumes, and what heights we're going to be flying at.
Stephenville Point. Then when we get there, we'll descend down to 6,000 feet and head north towards Goose Bay.
We're about to fly over an area that our computer models and weather information predicts should be about 2 or 3 days downwind from where the fires are burning in Western Ontario. So we're hoping to fly through these plumes that are produced by the burning trees and vegetation. When the plumes are first given off, they're black, thick black smoke with lots of chemicals in. But as the plumes spread out, they get much harder to see. And so the only way that we can see them is by looking at what our instruments say is happening to the chemicals in the atmosphere. Black carbon, particles of burned trees, essentially, nitrogen oxide, so NO and NO2, and carbon monoxide, CO. And now we're airborne and flying over Nova Scotia, and you can see there's lots of pine trees and forests below us, but there's really not a lot of houses or business complexes or anything. It's mostly just trees, lakes, and maybe the odd hill. So I'm at the back of the aircraft with Professor Ali Lewis, who is Professor of Atmospheric Chemistry at the University of York and Director of Composition for the National Centre for Atmospheric Science. Ali, why as UK scientists are we interested in forest fires in Canada?
Forest fires occur all over the world. They're quite natural, they happen all the time. What they do is they add a huge amount of organic material and carbon monoxide into the atmosphere. And the atmosphere swirls it around, and we're all part of this system in the UK. So what arrives over us has originated from North America and from Asia. So that's why we have an interest in what comes from Canada, because that affects what happens over Europe as well.
Nitrogen dioxide is primarily formed by combustion processes, so like in the engines of cars, in power stations. NO2 is important because it's bad for human health at low levels, it irritates the respiratory system, but also because it forms ozone. So when sunlight acts on nitrogen dioxide, you can get ozone forming. And that's why we're really interested in measuring the NO2 and also the species that it gets transformed into. Because again, at warm temperatures, these can re-release the nitrogen dioxide and you can get ozone formation a long way away from where your original plume was. There's some indications that we might be starting to see something now. So fingers crossed this is going to be the plume that we're looking for, and our tracers are going to start shooting up. So things like acetonitrile and black carbon, all the things we would expect to see in a burning plume. I'm talking to Johnny Taylor from the University of Manchester, who runs the SP2, which measures black carbon. So Johnny, can you tell me how it measures black carbon?
Well, we fire a high-powered infrared laser at the particles, and if they've got any black carbon in, then that'll absorb the laser light and they heat to incandescence, so we can measure the light from incandescence, and that tells us how much black carbon's in the particles.
The instrument I'm working on measures reactive nitrogen in the atmosphere. So inside our instrument we have a green laser, and this laser excites the NO2, the nitrogen dioxide, and then the excited state nitrogen dioxide emits light which we can measure, and that's proportional to the amount of NO2 that we've got. And now we're just coming into land in Halifax. It's been a really long day. First half of the flight was really good, and at least we saw the odd plume in the second half. So all in all, quite a good day, and hopefully some good science will come out of it.
The audio diary of Sarah Moller from the University of York. And we'll get some pictures from Sarah and put them up on our Facebook page. We'll also include a link to Sarah's blog from the expedition. And that's the Planet Earth podcast, featuring research funded by the Natural Environment Research Council. I'm Richard Hollingham. Thanks for listening.